to say, well, I just what do you think the value of the integral from 0 to 4 pi is? 0. That's what we say here.
So when we put them in composition, where I'm assuming they're going from that perspective to an arbitrary number or to infinity?
We're going to go to an arbitrary constant, and then we're going to take the limit of the arbitrary constant.
But the second one, do that say 0 to 2 pi?
Yes.
Okay.
And now we have 0 to 5 pi. 2. Now I know you might all be saying there's a pattern here, but let's just make sure. Let's do one more. What about from 0 to 6 pi? Oh, hey, that's 0 too. You totally actually evaluated that, right, Diego? And you're not just using the pattern or the pattern itself.
The pattern is good circle.
Pattern is good. So we're kind of in this situation where I have a positive area, and then that positive area gets canceled out by this negative area, and then that positive area gets re-put in, and then that positive area is going to get canceled again by another negative area, and then we get another positive area, another negative area. Keep going forever and forever, keep canceling areas. So when I ask you all, what this is, what are you going to say if this area cancellation is going on? 0. As far as engineering fields go, this is a result of engineering fields tend to use the indexer, the definition of sine of x dx. They use it because it just kind of works for the applications that they do. I am here to tell you all that they are all wrong. It's not so bad. That's an 8. That's also an 8. That's a sideways 8. Because we could, instead of starting off my little positive area, negative area cancellation little technique, I could instead just like save this for a second and go, hey, I have a negative area here. That's going to cancel it out with this positive area instead, and that's going to be 0. And then we're going to get another cancellation down here, which is 0, and another one here, which is 0, and another one there, which is 0. But this one that I set aside, the same, is always going to be there.
So for engineering application, you have that same power negative or something?
It depends on where you start it. So, yeah, exactly.
So, your question. Or different intervals, so you ever evaluate
Negative. Sorry.
Yeah.
Okay, because we're integrating over x axis. Right, which could totally go from negative infinity.
Remember what I taught you.
As far as application settings go, these are typically going to be like function transforms. So you already know a few function transforms. You know the derivative, and you know the acceptor. It may not be surprising to know that there are better function or more useful function transforms. One of these things is called the Fourier transform. Fourier transform is primarily used in signal analysis. It's a way of taking a function and turning it into a different kind of function that is meaningful or useful or another. Another one is the Laplace transform. There's the convolution integral. These are functions of functions to other functions. So that would be an application where you would actually set that function. So we got two different answers here. Now I want you to think like your best mathematical reasoning skills when you have a problem that has two totally different answers, but should only have one answer. What do you say the answer is actually? No. You can prove that though real quick. No. What do you actually say? I'm sorry?
I have no clue.
There's usually two letters you put next to each other, or you can use a word that begins with the letter U and rhymes with undefined. So what we can say here is the integral from 0 to infinity of sine of x dx is either undefined NA for not applicable, or a fancy math word, divergent. Math people did it first. And in particular, for a lot of the issues or a lot of the things that we deal with when we're working with infinity, usually this word divergence or divergent is preferred. For a sum, and I need you to remember that an integral is the limit of a Riemann sum. For a sum to be divergent means two different things, or potentially two different things. It means either that sum does not approach, and this is where we get sort of a two-parter condition, a unique real value. Real meaning it is defined as no one's right, like where it's at, no one's. And then uniqueness just means it's got to approach one number, only one. So this would be a particular case where this particular Riemann sum, or limit of a Riemann sum, is not approaching a unique real value. It's approaching two different real values. We don't have uniqueness. Or that sum is unbounded. Parenthetical, either positive or negative. So the top one means nil i's and also wants to approach unique numbers, not multiple different numbers. The second one means we don't want to attribute a value to some which is exploded to infinity. So no infinities, either positive or negative as far as an answer goes, and only unique one real number. picture x squared for a second. Right, we play the same kind of trick here. You know, we go from 0 to 1, we get like that tiny area. We go from 1 to 2, we get that slightly bigger area. We go from 2 to 3 areas even bigger still. Right, a whole
So there are infinite things that are added.
There are infinitely many things, and they're all getting bigger as we keep going. For the negative part, negative and negative squared. Reflect on the x-axis.
And if something approaches 0, then it is bounded. Like, instead of sloping out, it slopes this way and ends at 0.
It depends. It depends. We'll get to that.
Gotcha.
For a sum which does approach a unique real value, we'll say L. Then we can call this sum a new fancy word as well. That sum is called divergent, or not divergent, convergent. And the sum can be said to be equal to that unique real value L. So, you know, suppose for a second we did this particular antiderivative, you got an actual real number here, and there was only one, we can say that improper was equal to that. Reasons why that sentence is so weirdly phrased is because we are dealing with an infinite process, and we are including an infinite process. Zeno's paradox is a thing. I'm going to give them moderate detail with Zeno's paradox. Suppose you're on a football field, you're at one end of the football field, and you are only ever allowed to go half your remaining distance away from the other end of the football field. Do you ever actually get to the other end of the football field? Yeah, no, it's an infinite process. You keep taking half and half steps. Your steps keep getting smaller and smaller. Here's the problem. I can do the same thing with my hands. I have concluded the infinite process. That's why it's infinite. And why some people get kind of upset when we say convergence and so on. It's a paradox. It's a paradox, right?
Well, I was thinking because the speed of light is technically infinitely fast because that is.
It's not infinitely fast.
Because it is massless, so therefore it is.
But we know the value is, and it's not.
But it's not infinite, but
It's like
that's because
3
that's.
times 10 to the
But that's because that's the limit of the physics in which it exists.
And also, that's not even like a one-directional speed of light, it's the two-directional speed of light. Because like, we needed the information for speed of light to come back to the observer, which means we needed the two directions.
Right. Well, you have to do that, but then you also have the expansion of friendships and like that.
And like, just because we have the speed of light doesn't mean there are things in the universe that can't go faster than the speed of light.
Right, but nothing can travel through space faster than the speed of light.
Been one of those problems with 3 retries, and you get it wrong the first time, and your only options are converge or diverge. What do you think the answer is going to be? The other one? I think it's going to be the other one. So I got really annoyed at WebAssign because their questions kind of suck. Their questions kind of suck for a lot of things. I've had lots of problems with WebAssign in the past. So we have p integrals. We're integrating from 1 to infinity. We're determining values of p that make the thing either converge or diverge. Let's do our next one, which is integrating over an asymptote. And integrating over asymptotes tends to be, I've used this word in the past, I like this word because it's overly dramatic. They tend to be insidious. Looks totally fine. Right, Brendan? It looks totally fine. This interval could be your friend. You could go out and have a fun Saturday night on the town with this thing. This is what I mean by they're kind of insidious. If you take a look at this thing's graph, we got a vertical asymptote at 1 and -1. Let's see here, I plug in 0 to here. Plug in 1 here. So it's something like this. The area we're trying to get is this area. Now, to right around here.
Those areas don't have to cancel out of it.
Maybe they do. I don't know. I haven't done the integral yet. They could. The issue is that when you're going to go set up a Riemann sum, because you need to remember these integrals are limits of Riemann sums. You are taking a test point out of your subintervals and plugging that test point value for that subinterval into the function for the height of the rectangle. What if the number you end up plugging in happens to be 1? This thing's not defined at 1, which makes the whole entire Riemann sum completely undefined. So we kind of have that issue here. We cannot integrate over vertical asymptotes. So now this integral that was your friend Braden who went out on Saturday night and had a great time with, during the entire night they were talking crap about it. Doesn't feel good, right? We can't integrate over vertical asymptotes. Which means we now need to kind of invoke this power of limits thing using dummy variables again. But we're going to need to. One for the left-hand side of the vertical asymptote, one for the right-hand side of the vertical asymptote. So we need to split this thing into the integral from 0 to 1 of 1 over x plus 1, x minus 1 dx, plus the integral from 1 to 2 of 1 over x plus 1 x minus 1 dx.
It doesn't matter, that's defined at 1, because that's where
Oh, it's still gonna need limits. But we're gonna need now one side of the limits. we're going to need limit as b goes to 1. We're on the left side, so b is going to go to 1 from the left. So minus 1, or no minus sign up there. b 0, 1 over x plus 1, x minus 1. dx. And plus the limit as new dummy variable c
Oh, hell no.
goes to 1 from the right. 1 of c to 2. 1 over x plus 1, x minus 1.
Thank you.
And now you need to evaluate. You are given this integral to do. What method of integration you're going to use to get an anti-derivative? Okay, thank goodness. I was about to have a heart attack. What are you actually going to do, Blake? Yeah, this is partial fractions. Let's just go to the side, get our partial fraction decomposition, get our antiderivative. So we have a over x plus 1 plus b over x minus 1, 1 over x plus 1, x minus 1. A, x minus 1, b, x plus 1. B could go set up a system, solve that system. I'm just going to plug in singular values. If x is equal to 1, I get 0 here, and I get 2 here. B is 1. And if x is equal to negative 1, I get 0 here, I get negative 2 here. And a is negative. And then I can split up my integral. Negative 1/2, 1 over x plus 1, plus 1/2, 1 over 1x minus 1.
Bless you.
I have my back turned. I have no idea who sneezed. My guess, Diego? No. I have no idea who sneezed.
It was Solomon.
Oh, Solomon. Okay. Are you okay, Solomon?
Yeah.
All right, this is what we are working with. This is what we got going on. So let's come back here to this little thing. We have our antiderivative. Go ahead and plug in all of these numbers.
Oh, hell no.
Limit equals to negative 1 of negative 1/2 natural log absolute value b plus 1 plus 1/2 natural log b minus 1. And then minus, we're plugging in 0 now. For that first one, I got natural log of 0 plus 1, which I believe is natural log of 1. It's natural log of 1? 0. And then for that second one, I got 1/2 the natural log of 0 minus 1, which is negative 1. You have absolute value bars, so the absolute value of negative 1 is positive 1. It's natural log of 1 again. Plus, now we plug in 2 into that thing. Negative 1/2 natural log absolute value of, looks like 3. Plus 1/2 natural log of 2 minus 1. Hey, 2 minus 1 is 1 natural log of 1 is 0. And minus limit c goes to 1 from the right this time.
What?
Natural, no, 1/2, negative 1/2. Natural log c plus 1 plus 1/2 natural log c minus 1. Remember when I used the word to describe these? I said I might have been being over dramatic. What's that being over dramatic? Oh, this seems kind of bad. There's a lot of things here. Alright. If b is going to 1, are we going to run into any problems here? No. This is natural log 2. Are we going to run into any problems here? Yes. So let's put that one on hold. This one we're good with. All right, now C is going to 1. If I plug in C equal to 1 here, am I going to run into any problems? I'm going to get natural log of 2. So I have negative 1/2 natural log of 2. And am I going to run into problems here if I let C go to 1? Yeah, what's up?
Where is the second one of the second integral as evaluated as?
It picks up here. All right, we're plugging in 2 in our upper bound. So we get negative 1/2 natural log of 2 plus 1, which is natural log 3.
And the 0 will cancel out the question mark.
Yeah, and then when we plug in 2 in here, and I get 1/2 natural log of 2 minus 1. 2 minus 1 is 1. Natural log 1 is 0.
No, I'm talking the actual amount that we have, so 2, which is the natural log of 3 that we have there, I think.
Yeah.
And then the 0, which is just gone.
Yeah, because if I plug in 0 into this thing, I get natural log of 1. And if I plug in 0 into this thing, I get natural log of the absolute value of negative 1.
Oh, which is, yeah, sorry.
Lots of things went to 0 here.
What we just saying? That might have one part.
So here, this one is minus, right? We just need to figure out the fate of those 2 limits. All of this stuff is unique real number stuff. We got these. And we have a subtraction sign.
Question before you erase this part. Could you explain how you went from that second line to the next? Like basically where you started doing the scientific notation.
Oh, from here to here?
Yeah.
I take away 1 from this thing. Right, and I did that. Which is -1 to the negative, or times 10 to the negative 18. Right? So that gets divided down. And then I have x to that power. Okay. From here to here, I plug in b, and I get this thing.
Wait.
Right,
Okay.
upper limit's b. Then I plug in 1, and 1 to this power is 1. Right, 1 to any power that isn't infinity is 1. So, I get that. And then I evaluate b going to 0. Or not b going to 0, b going to infinity. I'm dividing by infinity here. 1 over infinity, that's 0. And then that sticks around.
Alright. It's, my brain is still trying to like wrap around it, but
The big picture here is that it works.
yeah.
Right? The big picture here was writing out equals. Let's pull up the 1/2 because we're going to kind of pull this one. When b goes to 1, b minus 1. When c goes to 1. C minus 1.
Same thing, a bunch on both sides.
What?
Same thing, a bunch on both sides. This little same thing.
Yeah, that's what it's going to end up being, but we do have a little bit of shenanigan because these are technically one-sided. If b is going to 1 from the left, that means this thing inside the absolute value bars is negative. Because we're going to be from the smaller one side. So if I had something smaller than 1 and I'm subtracting 1 away from it, I'm in the negatives. So I want to kind of get rid of these numbers. Our goal is to make this into 1, not 2 units. No, this one. Right, I'm trying to not forget about these two technically being different on sides. And then this one, if I'm coming in from the right, I'm coming in from bigger than 1, which means these numbers are bigger than 1. When I subtract 1, I get positive numbers still. Right now. So these absolute value bars are not doing anything. And if both of these are going to 1, then I can just pick 1 to use, right? One variable. I want to take these two different ones, these two different W variables, and put to 1. So we can use it. Also, I forgot my natural ones, didn't I?
Yes.
Alright, we got this thing going on here. This is where log rules are going to happen. Limit b goes to 1. Natural log. This one's positive, so it goes on top. This one's negative, so it goes down the wall. Diego doing okay? Log rules. A little bit. All right, we do have a natural log here. Is a natural log a continuous function? Yes. You remember your rules of continuous functions being able to pull limits inside of continuous functions? Natural log of limit as b goes to 1, 1 minus b, b minus 1. What?
I don't know, just -1. That whole fraction. Crazy.
No, not really. Not really.
Not really?
Not really. Although I feel like I kind of screwed up here. Yeah, the limit is b goes to 1. 1 minus b over b minus 1. And I want to take this thing's limit. What's the limit at the top? 0. What's the limit at the bottom? 0. How are you going to take a limit when you're at 0 divided by 0? Both equals 1. What's this thing's Stoff's derivative? Negative. And what's the derivative of the pot? This is where I think I've been a little bit too cavalier with my absolute value promise. You think I kind of want to do it? That's it. So you get natural log of 1, which is 0. Which means back here in this case, we got 0.
That's not even 0 minus 0.
Can you have done a L'Hopital's rule thing over here?
Well, no, like, because you could, because I was looking at it, like, if you have, approaching 1 from the left, it'd be like, negative 0.0001. Then on the C1, that would be positive 0.0001.
Remember, that's going to be inside the log. Your natural log of 0 is still.
Right, but it's not 0.
Yeah, it's not.
It's a finite value minus finite value. Like, but not like, but they're equivalent. One from the
Yes.
one from the right. Because of that, the values will be calculated.
Yeah. And then there's subtractions. Yeah, exactly.
I might be a little slow, but when you have that natural log of the limit b to 1, and you have your stuff right, the whole fraction, right?
Yeah.
On the numerator, why, I don't know what we're writing here, why can't you just make that b minus 1 by taking a negative out? And just have it look at that itself.
Because it didn't. If I'm being totally honest, and like, if you haven't picked up on this fact, I probably shouldn't be looking at my own examples all the time.
Okay.
I made this example up all the time.
Okay. I'm like, we're
I went, I can do this. But I didn't really think about the ramifications things of, I can do this, yeah, I can do this.
I was like, we were done right there. Why are we still going?
Because
Okay.
he did get there eventually. This is one of the reasons why I kind of made this like comment last week of I don't want to rush my way out of chapter 7. Because you can imagine the terror that would ensue if I said, okay, we're done with chapter 7 now. No, I want to do more of this stuff on Wednesday. And then we're gonna do like the like sort of kind of important but also like not really that important stuff on Alright?
We got problems tonight or not?
You do, yeah.
Hopefully not. Thanks, King.
Everyone's gonna be here. So, the next one is. What's up? Remember you were saying last week, you got back to
That was the longest I stayed on live, y'all. It's only because I didn't go live with y'all when I went to Tropical Smoothie. We didn't have our lunch date. And I had woke up late. I took a nap before I got here. So I had just woke up before I had to come here. I had to hurry up and rush to Tropical Smoothie. I was 10 minutes late to class. But good thing he wasn't really going nothing over. Oh, we got our quizzes back. I got a 9 out of 10, of course. Hello, it's a game. So yeah, there's that. I think I kept having some things and stuff like that. Hey Queen, thanks for the gifts, babe. Yuntie man. Why everybody always talking about my braces? Like, damn. Do they look cheap? Do my braces look cheap for real? Because I spent a pretty penny, man. I spent a nice little penny. I'm going up, honey. I'm going up. I'm going up. I want the world to know. We finna lose service for like 3 seconds, okay? Slime, shut the fuck up. Spamming that, for real. Shut the fuck up. Oh, I gotta throw away my smoothie now. Ooh. Y'all, I ain't gonna cap. Anybody that say anything about Ekane, everybody say they read, even if they didn't eat. Like, please, y'all say everybody eats everything. Y'all don't really know what a read is, Queen. Like, seriously. I'll be expecting some good shit. And it don't ever hit. I'm sorry. Y'all just ain't used to bitches coming to me. You know what I'm saying? Y'all ain't used to bitches coming to me because of that. No, I'm not washing my hands, so leave me alone. I'm gonna wash my hands. Let me go in it. Okay. Let me wash my hands. Hope no one heard me. I hope no one heard that. Why would I wipe the toilet? I didn't pee on the toilet seat. I know how I ain't from women. I ain't get my, oh, today is Monday. I am supposed to have my balls installed, but I don't, Queens, I don't have my balls installed and I got out not today. I could sit down and pee today. Whew. Whew. Oh, that nap I took before class did me no justice. Did me no justice. Ooh, girl. Medicaid braces don't even exist. It's always bitches with fat ass teeth and they mom talking about somebody with braces. Bitch, you only got fake teeth because you needed braces. The hell? What's really going on? Like, my bad I ain't fuck Rick Ross fat nasty ass. I'm sorry. My bad. And honestly, let's be so for real. Chris look better than Rick Ross. Chris look better than Rick Ross. Quit playing. Quit playing. So Chris don't look better than Rick Ross. Like, cut it out. Cut it the fuck out, bro. Chris look better than Rick big nasty ass. I'm sorry. I'm fucking sorry. Y'all playing games now. Y'all playing games. Y'all hating. Y'all mad. No, y'all is mad. Cause ain't no way. Chris looked 10 times better than Rick Ross. She said I was 24 driving $200,000 car. Bitch, add me up. Duh, I would hope you driving a $200,000 car. You fucked his fat nasty ass and he was a millionaire. You better be driving $200,000 cars. You better be. Bitch, I'm in a $150,000 car. Baby daddy ain't rich. I got this shit off the hustle, the muscle, off my name. Not no nigga name, okay? You only had that car because you're a baby daddy. I got this car off me. $150,000. No, it ain't $200K, but you ain't talking to them broke ass bums you be arguing with on TikTok. I get money for real. I get money for real, Yuntie. So you mad because you an old bitch that clap her cheeks on TikTok all day and prank call bitches. I don't care. I said what I said. I'm not going to be 50 years old clapping my ass and prank calling on TikTok, bum. Fuck is you saying? I got a Versace robe too. I can shake my cheeks too. I'm 25. Is you cool? Bitch. You ain't doing shit special. You better have a $200,000 car and you fucked his fat nasty ass. You better. You better be driving something like that. You ain't doing shit different than me, queen. Cause I'm really doing it. You feel me? I'm really having. Not off no rich baby daddy. This me. This Ekane you talking to. This Ekane you talking to, queen. I ain't fuck no fat nasty ass rapper to get no money. I didn't. I didn't. I'm sorry. Hold on, Moosies. Hold on, Moosies. I wish I could fuck Rick Ross big ass, psych. I wish. But I said what I said. You call Nicki Minaj childish because she doing what she doing, but you sit your old ass on TikTok live entertaining 16-year-olds and calling people baby daddies. Bitch, you're childish. And I'm still not gonna be your age doing what you do on TikTok. Fuck is you saying? Me and you was doing the same shit when you was 24. You driving expensive